topics and those non-dimensional numbers only with practice. So not just for this subject, for any subject, practice is important, and only with practice you will be comfortable, you will be confident. Okay, so that's about the CAT 1 examination. So the class average is uh, about 16, slightly less than 16. The maximum mark is 28, and the minimum mark is, I think, 7. 7 is the minimum mark. Okay. Moving on, we'll go on with the present module that we have already started. This is the module number 3. What we have covered in module number 3 is we have taken up two-dimensional steady-state systems. The first method that we have seen in two-dimensional steady-state systems is the graphical method, using which we solve some problems. Then there's also a numerical method for solving two-dimensional systems. I will take it up after I complete the transient system. So I mentioned that it takes some time for you to grasp the concept of a two-dimensional steady-state systems using the numerical methods, and I said that I will take it up later. So I will take it up later towards the end of this particular module. We have jumped one topic and started the lump systems, which is the first one among the transient heat conduction systems. Now remember, we are dealing with one-dimensional transient systems. We are not gone to two-dimensional, we have not gone to three-dimensional. So what we have initially seen is steady-state systems, one-dimensional steady-state system, then two-dimensional steady-state systems, then one-dimensional transient systems. So among one-dimensional transient systems, there are some applications of one-dimensional transient systems. There are three different classes of problems we can put. So those classes of problems fortunately have an what we call analytical solution. So that's why we always like analytical solutions, because analytical solutions are applicable at every point in the domain. That's one thing. And also analytical, when you are able to solve some problem analytically, it gives you some confidence. It gives you some satisfaction, because you are able to apply all the mathematics that you have learned, all the concepts of calculus, ordinary differential equations, partial differential equations. Those concepts, if you are able to apply in solving a problem, an application, engineering application, then it gives you some confidence, some satisfaction. So that is the importance of analytical solutions. Fortunately, there are analytical solutions available for one-dimensional transient systems, just like we have seen for the lump systems. As far as lump systems are concerned, the basic concept of lump system is that it doesn't have any thermal gradient inside. That means dt by dx is 0. So because of that reason, we cannot use the heat conduction equation to solve for the lump system, because heat conduction equation is based on the presumption that there will be some thermal gradients inside the body. But lump systems, the thermal gradients are minimal, because of which the heat conduction equation cannot be used. But for the next two types of or categories of one-dimensional transient systems, the heat conduction can be used and the analytical equations can be applied. So these two systems, they are called non-lump systems, or they're also generally called as a distributed systems. Distributed system is there is a temperature distribution inside. In a lump system, there is no temperature distribution inside. There are no different temperatures at different locations. There's only a same temperature at different location. Whereas in case of the other two systems that we are going to see, there will be a temperature distribution. Temperatures will not be uniform throughout the domain. So for that, we will see what are the analytical solutions, and we'll see where they are applicable. And towards the end of the class, I will also tell you how to distinguish between a lump system and the two other systems that we are going to see. Sometimes it becomes a tricky part. See, as of now in CAT 1, we covered only lump systems. So logically thinking, I will ask a question only on lump systems. The other two are not there. So if you check for Biot number, it will be a lump system. But what in the final examination, it won't be clear whether it's a lump system or not. You will have to find out whether it is lump or some other thing. So there are some rules of thumb or some phrases to distinguish a lump system from a non-lump system. So how to do that? All that stuff we will see in today's class. So I'll share my presentation. So in the first class of the transient systems, we have seen that the transient systems are categorized as three types. The first one is a lump system, where there is no temperature gradient inside the object. Then there are the infinite solids, and then there are semi-infinite solids, infinite and semi-infinite. So totally there are three. The first one is uh, let me first one in transient. First one is lumped. Second one is infinite body. This also we can call it as lumped body or lumped solid. And the third one is a semi-infinite. All these again are one-dimensional transient. They are not two-dimensional transient or three-dimensional transient. They are only one-dimensional transient. So in today's class, we shall see the next two. So I'll try to complete the theory part of these two, and then if time permits, we'll take up a problem, or we'll take a problem in tomorrow's class. Now we'll take up the second one, infinite body. So most heat transfer problems can't be treated as the lump systems. Yeah, because there will be temperature gradients in most cases. Hence, thermal gradients are considered in the following geometries. So among the infinite bodies, there are again three types of standard geometries. See, why do we choose the standard geometries is because you remember when we derived the heat conduction equation, what we have seen is there is one form in the Cartesian coordinates, one form in cylindrical coordinates, and one form in the spherical coordinates. So Cartesian coordinates is directly applicable for the plane wall. Cylindrical coordinates equation applicable for infinite cylinder, and the spherical coordinates applicable for this spherical shape. So these three are standard shapes for which we have the equation. We have the fundamental governing equations. Therefore, we consider these standard shapes. So this infinite bodies applicable to infinite bodies which are in this are considered here. So what are these infinite bodies? What does this word infinite mean? Infinite means, is it such a big thing that it becomes infinite? No. What it means is that uh, the one dimension, let us say, let us take a plane wall. Here's a plane wall. I will draw this plane wall here. Let us take a huge corridor of, let us say, Red Fort of India. It's a huge construction, and you can see, let us take this wall. Let us assume this is the wall of a Red Fort, wall of the Red Fort. Okay. Now, compared to this thickness, the thickness of the wall, the length of the wall and the height of the wall are very, very large. So length tends to infinity, height tends to infinity, whereas this thickness does not tend to infinity. It has got a finite value. So such objects are called as infinite bodies. Okay. Then what are the semi-infinite bodies? Sometimes this nomenclature can be confusing, so I'll try to clarify this later. So as of now, when you are told about an infinite body, just keep in mind this particular example of a wall. Let us say this is the wall of China, the Great Wall of China. Great Wall of China has got a finite amount of thickness, but extremely large length and height. So the thickness may be a few centimeters, maybe 1 foot thick, but the length can be few hundreds of kilometers, and the height could be few meters. So compared to the thickness, the length and height are very, very large, and they are extending to infinity. In mathematical terms, we can say that compared to the thickness. So they are called as infinite bodies. Similarly, infinite cylinder and infinite sphere also. So in a plane wall, if the thickness is small compared to the width and height of the wall, it is treated as an infinite plate. So here you see this is the cross section of a wall. This is the thickness of a wall and other dimensions. The length and the wall of the width of the wall are extending to great amounts or great lengths, and therefore they are tending to infinity. That's what we can say. So you see here, this wall is represented as a rectangle with a central axis and x being measured from the mid plane. X measurement is from the mid plane. So you can see the thickness of the wall is L plus L. This is 2L. And the measurement, the axis is located at the center, and it can vary from 0 to L and also from 0 to minus L. Now this wall is subjected to a convective condition on either side. Let us imagine a convective condition. So on one side there is a T infinity and H, and other side also it's T infinity and H. So there are two same convective conditions on either side. And this wall is at an initial temperature of Ti. Now this can be considered as a huge, a large aluminum plate which is being subjected to surface treatment or a heat treatment in a furnace. So after the sheet is rolled, if it is loaded into a furnace, and the length and width of the plate are extremely large compared to the thickness, and the thickness on either side of the thickness, we have this uh, same heat transfer coefficient and the same temperature. So this is a typical example of an infinite plate. Okay. So in such a case, there is an initial temperature of the plate, and then suddenly it is subjected to this kind of a convective conditions. So what will happen? The temperature will either drop or rise depending on whether the initial temperature is greater than the ambient temperature, this convective temperature, or lesser than the convective temperature. So the question will be, after 10 minutes, what will be the temperature of the plate? And that is not just after 10 minutes. Let us say this is a way of expressing the condition. You see here, temperature as a function of x, that means as a function of space, and other one 0. The second one is actually this is space and time. Space and time. So in this case, x is x, that means at any x, at anywhere in this region, initially, that means that time is equal to 0, temperature is Ti. That means if you have just rolled a aluminum sheet, probably its temperature, initial temperature is probably, let us say, 200 degrees Celsius. So anywhere at initial at T is equal to 0, the entire sheet is at 200 degrees Celsius. But then it is loaded at that temperature, it is loaded into a furnace, which is maintained, let's say this furnace is maintained at 300 degrees Celsius for some heat treatment purpose. So what will happen? The temperature of the sheet will keep increasing in this case. So from 200, it will start moving towards 300. But then what happens? The temperature at the surface will be close to 300, whereas when you go away from the surface towards the center, like this, the temperature keeps keeps moving far away from 300. It will be close to 200. That means as the time passes, the temperature inside the object will keep changing. So the change also will be different. So the questions can be, what is the temperature at any x and at any time? For example, the temperature at x is equal to 0 and time is 10 seconds is how much? X is equal to 0 is the center plane at 10 seconds. Similarly, what is the temperature at x is equal to 5 millimeters and 15 seconds? So 5 millimeters is, let us say, somewhere here. And at 15 seconds, what is the temperature? So you can see that the temperature now is a function of space as well as time. In contrast to the lump systems, the temperature was only a function of time in lump systems. Spatially, the temperature was uniform. there were no temperature gradients in lump system, whereas here there are temperature gradients. So this is the basic difference between the lump system and the distributed system. This is called, this system is called as a distributed system because the temperature is changing with respect to time and space also. So if I try to plot, the temperature, let us say at this is the axis, this is the x, and this is the temperature axis. If I try to plot the temperature versus distance for this, what happens? See, initially the temperature, temperature at everywhere in the plate is 200 degrees Celsius. So initially the temperature is uniform. This T or tau is equal to 0. This is 200 degrees Celsius. After that, the surface has been subjected to 300 degrees Celsius. So what can happen? The temperature can rise like this. After, let us say this after, at the instance of 10 seconds. The temperature at the surface has increased to 300. So this value is not necessarily 300. It may be, because instantaneously the temperature in 10 seconds may not reach 300. So it is probably 280 degrees Celsius. Then again the temperature will increase after 20 seconds. Again that there will be temperature rise in 30 seconds. So you can see 40 seconds. You can see that the temperature is changing both with respect to space and also with respect to time. So time is increasing in this manner. Time is in this graph, time is changing from 0 to up to 40 degrees. That's what I have shown here. And you can see that the surface temperature is quickly approaching this 300 degrees, the ambient temperature, whereas the interiors are still cold, because of which we will have thermal gradients. And this is distributed system. This is called as a distributed system. Okay. In contrast, if this plate has been a lump system, the temperatures would have been Tx. So initially 200 degrees Celsius, then 220, then 230, then 250. You can see the time, as time is increasing, the temperature also is increasing, but temperature is increasing uniformly. So there are no temperature gradients. If you evaluate the thermal gradient on any instant, you will get it 0, because at any point the temperature is the same. Whereas in this case, there is a thermal gradient. So this is the distributed system, whereas this is a lumped system. So this is the way you need to understand the concepts. Okay, now the questions are, what will be the temperature at any point? What will be the temperature at a point at a given time? So that will be the, so you will be specified what will be the location and what will be the time. At that you will have to find out the temperature, or vice versa. At what will be temperature may be given, you may be asked what will be the time taken for the center to reach that temperature. So it can be asked in any way. So there are ways to solve it. Okay, so let us say we want to solve it using analytical methods. Now what the starting point is always the conduction equation, because the thermal gradients are there, we can go for the conduction equation here. So dou square T by dou x square, this is the diffusion term, and 1 by alpha dou T by dou tau, this is the transient term. So temperature is changing with time and temperature is also changing with the distance. Therefore, this is a partial differential equation, and it is a second order equation. Therefore, we will need two boundary conditions. And since there is a dou T by dou tau, we also need one initial condition. So the initial condition will be temperature at time is equal to 0. There is a certain initial temperature. That will be the condition. So that condition we can take. So this condition we can use. This is the initial condition. The boundary conditions can be, you see here, because there is symmetricity on either side. There is the same convective conditions on either side. The center will behave as an insulated surface. Therefore, at the center, that is at x is equal to 0, dou T by dou x will be equal to 0. Because at that point this is insulated. So whatever is happening on this side, there will be a mirror image of that happening here. So at this point, the dt by dx will be equal to 0. And at the surface, we have convection heat transfer. So K dou T by dou x. So K is conductivity of this material multiplied by dou T by dou X. The thermal gradient at the surface at X is equal to L. That is at the surface. This is the heat transfer due to conduction or heat flux due to conduction should be equal to the heat flux due to convection. So heat conducted from at this point should be same as the heat convected. If you take a control volume at this point, and write the energy balance equation, heat conducted is equal to heat convected. So that is what this is. So these are the two boundary conditions. So with one initial condition and two boundary conditions, we can solve this equation. We can also non-dimensionalize the temperature as you see here. Theta is the non-dimensional temperature, which is theta divided by theta I. Theta I is the initial temperature difference and theta is the instantaneous temperature difference. So with this, we can solve it. It involves, it needs a lot of knowledge in solving partial differential equations, calculus. People have done it, and this is the solution. So as per our syllabus, we don't need to need to know how the solution is obtained, but we'll see how the solution is and how it looks like. So theta star, that is the temperature distribution or the non-dimensional temperature, is given as a, you can see sigma here, sigma n is equal to 1 to n is equal to infinity. That means this is basically a infinite summation series, and Cn some constant with n. So as n is equal to 1, this will be C1, n is equal to 2, C2. Then there is an exponent term, and then there is a zeta n, again n, this value of n. If n is equal to 1, then this will be zeta 1. Zeta n whole square multiplied by Fourier number, that multiplied by cos of zeta n multiplied by x star. X star is the non-dimensional distance. This one, x by L, x star. Okay, so the temperature distribution is obtained in this way. But then what is Fourier number? We have seen this Fourier number. It is a non-dimensionalized time, alpha tau by L square. The Cn value is this in terms of zeta n, 4 sine zeta n divided by 2 zeta n plus sine of 2 zeta n. And what is zeta n? Zeta n is the root of this equation. You can see here, root of this equation. This equation is in terms of zeta n, tan zeta n is equal to Biot number. So you can see in the entire thing, there is a Biot number coming and the Fourier number coming. Okay, so Biot number in this one, Fourier number here in this one. So with the known Biot and Fourier numbers, so we can find out the root of, find the value of zeta n, substitute zeta n here, find Cn. So substitute Cn here, find Fourier, Fourier here. So knowing Cn, zeta n, Fourier, and the non-dimensional space, you can find out the first term. Likewise, you have to sum this to infinite number of terms. So infinite number of terms summing is not necessary. I mean, it's not possible also. So what we do is we go for a finite number of terms. Let us say maybe 5 terms or 10 terms, depending on the accuracy we need. The subsequent terms, the later terms contribution to the exactness of the solution is usually low. So we usually stop at the first 5 terms. Okay, but you see what is involved. Even for the first 5 terms, you first start by evaluating the Biot number, and then find the root of this equation, substitute it here, find Cn, substitute here, then find the Fourier number, substitute here, and so on and so forth. So because of this, even if you have the analytical solution, it becomes complicated. Now what's the other problem is that this entire thing is evaluated at a constant properties. You see here, alpha is the term. Alpha is K by rho Cp. The alpha is the thermal diffusivity, which involves some properties, and all these properties are supposed to be constant. So the temperature variation is very large in this entire domain. If the temperature variation is large, the thermal properties will change, and the alpha will not be constant. That means whatever equation you are seeing now is applicable only for. So this is a limitation for this one-dimensional. Only then you can apply this equation. Likewise, equations are available for infinite cylinder also. Infinite cylinder is one in which the conduction is in the radial direction. So the length for infinite cylinder, the length is extremely large compared to the radius. So infinite cylinder very long. So typically L by R is greater than or equal to 10. This is an infinite cylinder. But anyway, we will have to confirm it after calculating the Biot number only. So for any transient conduction problem, the first step is to calculate whether it's clumped or not. So I have to calculate the Biot number. So if it is less than 0.1, it is lumped. Otherwise, it can either be infinite object or a semi-infinite object. We'll have to decide. Now, infinite cylinder is one which has conduction in the radial direction. For an infinite cylinder, L by R is greater than or equal to 10. So only then we can treat. So this is the typical condition of the infinite cylinder. This is the initial condition. This is the non-dimensional geometry, non-dimensionalized radius. This is the convection condition. And if you solve for this using the analytical solution, this is the exact solution. Okay. This is, you see, for Fourier greater than 1. This is another condition also. Here also, for Fourier between 0 and infinity, valid for any time. Likewise, here Fourier greater than 0. So for this, that means for any time, this equation can be applied. Okay, but again, you see here, Fourier has to be calculated, Cn has to be calculated. Again, you have J1, another root. That root has to be found out from this equation. And remember, it is not simple. This J is a Bessel function of the first kind. Again, you have problems here. Okay, so we'll have to find the root of this equation, substitute it here, and make all the substitutions here, and do an infinite series summation, or at least the first 5 terms. So this is another solution. But we'll go back to this. What happens is, this infinite solution is needed when the Fourier number is small. People have found out that for a Fourier number greater than 0.2, the first term approximation is sufficient. That means n is equal to 1. If you can take the first term only or first term alone for Fourier numbers greater than 0.2. So that means for Fourier greater than 0.2, the subsequent terms don't contribute much. Therefore, you can ignore them and take only the first term. So this Fourier greater than 0.2 has to be ensured, and if it is greater than 0.2, you can evaluate only the first term, and that is good enough to give you the solution. Likewise, for the cylinder also, for Fourier greater than 2, you have the first term approximation. This is called as first term approximation. So here, instead of going for infinite number of terms, you evaluate only the first term, and it is good to go. So that is sufficient, but it comes with a condition: Fourier is greater than 0.2. That means after a certain time only this is valid. Similarly, for sphere, you have the same type of equations. So the same kind of procedures are necessary to calculate. Again, there is also approximate solution for Fourier greater than 0.2. So you have to evaluate this. Even evaluating this is not so easy, because you see, you have to find out the root of this one. This equation is not a straightforward equation. There is a caught here, and therefore there is a trigonometrical function involved, and makes it non-linear. And in fact, this becomes what is called as a transcendental equation. Any equation which contains logarithms, exponents, trigonometric functions is called as a transcendental equation. A transcendental equation is not easy to solve. You may not have a analytical solution for that. You may have to go for a numerical solution. So that makes it difficult. So fortunately, what happened is, one person called Heisler took the time and effort to evaluate this one-term approximate solution and put it in the form of a graph. These are called as the Heisler's charts. So we shall see what are these Heisler's charts. So these are basically the graphical solution for the first term equation. So for this equation, the plot is given. That means the person has evaluated and put it in the form of graphs, so that we don't have to undergo the trouble of calculating this. Okay, so that is done. Now, if you want to still use this equation, what is necessary is you need to know the value of zeta 1, and zeta 1 is depending on Biot number, and also you will have to find the value of C1. So if you have a Biot number, you will need the zeta value and C value. So this zeta value and C values are tabulated, and as you see here, for different Biot numbers, For a plane wall, the value of zeta 1 and C1 are tabulated. Similarly, for infinite cylinder, zeta 1 and C1 are given. For sphere, zeta 1 and C1 are given. So you can see that some people have taken the pain of solving this equation and substitute and finding the value of C1 for different values. So these are readily available. So all you have to do is read from the table. Unfortunately, this table is not there in the data book, but this table will be available in textbooks of heat transfer, the standard textbooks of heat transfer. But remember, this is applicable for Fourier greater than 0.2 only. That means this is the solution for the first term approximation. These are called as the first term approximation solutions. But this man Heisler has made our job easier. He took those first term approximation equations and plotted them in the form of charts. So charts are there to determine the center plane temperature and any other plane that are available separately, and also Grober charts. So there are Heisler charts are helpful for finding out the temperature. Grober charts are helpful in finding out the heat transfer. You see here in this equation, this is the equation to calculate the heat transfer. So this equation is available in Grober charts. This equation is available in the form of charts. This is in the Heisler chart. So and this in the Grober chart. These charts are available in your textbooks as well as the data books. So here I have given a typical Heisler chart for finding the temperature of a plane wall at mid plane. There is a wall at the center. I want to find the temperature. So you see here, this is the graph, and this inset is a magnified version of this region. Okay, so basically this and this are same, but this region being very cluttered is presented here. So you can read the temperature of the center using this particular chart. All you have to do is on the x-axis found the Fourier number. Fourier number can be found using the time, and you have to find the Biot number, and the Biot number is the parametric is a parameter used to plot these curves. So once you have this Biot number and the Fourier number, you can find. For example, after let us say our Fourier number is this one, and Biot number is let us say Biot number is here 6. Bio is 6. Let us say Biot number is 6. So I'll draw a vertical line here up to Biot number 6, and I'll read the value on the y-axis. You see here on the y-axis there is a temperature differences ratio given, using which I can read the value of the center temperature. So this is for the mid plane. Okay, be careful. This is only for the mid plane, but there are other locations also. So at Heisler chart for a plane wall at any plane, not necessarily the mid plane, but any plane. That means other than the mid plane. If you want to find out, you have to use this. So for this, on the x-axis, you have Biot number. On the y-axis, you have the non-dimensional distance. On the parameter, you have the non-dimensional distance. On the y-axis, you have the temperature difference ratio. So again, knowing the Biot number, you can drop a vertical line, and here we can read it like this. Okay, so this is how you will use these equations. Likewise, the Grober charts can be used to find the temperature, find the heat transfer. So Q naught, what is Q naught? Q naught is the maximum temperature, maximum heat transfer possible, and Q is the actual temperature. Q naught is the maximum heat transfer possible, which is possible at the initial conditions, and then Q is the actual heat transfer at a particular instance. So using this, you can also find the heat transfer. So this is the Grober chart. Okay. So likewise, we have charts for cylinder as well as sphere. So infinite cylinder and sphere also we have the Heisler charts as well as Grober charts. So where to find these charts? You can find these charts in pages from 74. 74 to 82. Data book pages 74 to 82. You will find this Heisler as well as a Grover charts for the three geometries: plane wall, cylinder, and sphere. Okay, the problems will take up later. Tomorrow today we cannot do them. Now we'll come to the next solid, next type of solid called as the semi-infinite bodies. So what is this? A solid that extends to infinity in all but one direction is called as a semi-infinite solid. So don't go by this definition. Sometimes it gets confusing. So what is this? I'll explain what the semi-infinite bodies are. But analytical solutions are may be obtained for the semi-infinite bodies. Again, it's a one-dimensional transient, but it is a different kind of a body, semi-infinite body. So if a sudden change of condition is imposed on a surface, the transient 1D condition will occur, and the solution for infinite solids are valid, but several terms must be considered. But then there are simpler solutions available for Fourier number greater than 0.2. Now for the semi-infinite bodies, now you can see here there is some random shaped body, and on this surface, let us say some thermal condition has been applied, like suddenly we started condensing steam on this surface. So what happens is this surface feels the thermal effects. It feels the temperature changes, but you can see the other directions, they are extending to infinity. See, sir, these are extending to infinity. Therefore, these other sides are quite far away from this plane surface. So whatever is happening on this side may not be felt on this side. So when we are talking about the large bodies, this is possible. So in such bodies are called as the semi-infinite bodies. So in those bodies where the thermal effects of one side are not felt on the other extremes, or they may take a very large time, very long time, like few days, months, sometimes years. That kind of a bodies are called as a semi-infinite bodies. So here you see some semi-infinite bodies and how the temperature distribution looks like. So here there is a semi-infinite body. On one side of it, the temperature has been made constant. It is subjected to a constant temperature. So what happens? Initially, the time at time t is equal to 0, or initial time, we have this temperature distribution, and as time increases, the temperature keeps changing in this pattern. Similarly, another condition that is possible is at this surface, we can subject this surface to a constant heat flux. So in such a case, this is the temperature distribution. You can see here at this phase, now the temperature is not constant. It actually keeps changing with time. Whereas here, this side, the temperature remaining constant because we are maintaining by some method, we are maintaining the temperature constant on this surface. So this temperature remains constant, but interiors, the temperature keeps changing. In this case, we are maintaining a constant heat flux, not constant temperature, because of which the temperature is changing even at the surface and of course in the interiors. Here you can see the temperature, the surface is subjected to a convection condition, because of which the temperature at the surface is changing and also the interiors is changing. But far away, as you move far away, the time taken is very, very long. So typical semi-infinite bodies are very, very large bodies. So here you see there is a temperature distribution in a semi-infinite solid for the condition of the constant surface temperature. So for this condition, is the equation. This is the temperature distribution, and you can find out the temperature at any point and time, provided you evaluate the right hand side. This ERF is what is called as the error function. So this error function is a mathematical function, which again is determined in the form of tables. So there is an equation for error function. The value of this error function can be read from tables, which is available in page number 68 of your data book. So once you have found out this error function value, you can substitute here and find out the temperature. So again, this solution is complex, therefore we are not going into the solution, only the final equation is given. Unfortunately, there are also graphs for this. Now this is the value of the heat flux, which can also be calculated. Similarly, for a constant heat flux surface condition, this is the equation for temperature distribution, and you can see it is a little bit complicated compared to this. And for surface convection, This is the equation, and you can see it is slightly even more complicated compared to the first one. So because these are complicated, people have developed graphs. So these are called as the graphical solutions. So for these graphical solutions are applicable for semi-infinite bodies, not infinite bodies. So you can see on the x-axis you have x by root alpha, which is one parameter, and the curves are plotted as a function of h root alpha t by k. Okay, so this t is the time here, not the temperature, it's the time. So here there is time coming up, here there is time coming up, and using this you can find out the temperature at any particular location. Okay. This is for the convective conditions. So we have this graphs for finding in the convective conditions. Also, when the temperature is known, we can find the time. So this charts related to the semi-infinite object are given in page 69 to 71 in your data book. Okay, using this you will be able to find the values. Now, in any real world situation or in the examination conditions, you will not be told whether it's a lump system or a semi-infinite or an infinite system. So how to distinguish? So I have tried to put some hints here. There are in general, there are very general hints, and they are in general applicable, and they are also fine. But there can also be some exceptions. But we'll go by this. So there are three types: lump solid, infinite solid, and semi-infinite solid. So if you calculate the Biot number of a lump solid, it will be always less than 0.1. But for infinite solid and semi-infinite solids, provided if you are able to calculate, they will be greater than 0.1. Okay. Then what will be the size? Lump solids, by their definition, they are supposed to be small, because the temperature has to be uniform. For that, the object must be small. So you are talking about few millimeters. And you are talking about the lump system. Few millimeters, small size or extremely large thermal conductivity. That is the requirement. Okay, so lumps solids are generally small and compact in nature. Infinite solids are larger than lump solids, and semi-infinite solids will be huge, very, very big. Okay, so what are the dimensions will be that are provided? So sometimes given depending on the dimensions available in the problem, we can also tell whether the object is a lump or other. In the lump solids, all the required dimensions will be provided. For example, if we're talking about a slab, rectangular slab, then all the three dimensions will be given. All the three dimensions will be given. Whereas for a cylinder, radius and length will be given. For a sphere, only the radius will be given. So all the required dimensions, see, for rectangular slab, 3 dimensions are needed. For cylinder, 2 dimensions are needed. For sphere, only 1 dimension is needed to completely define them. So all the necessary dimensions will be given, and that is a hint of that being a lump solid. But you should also verify the Biot number. That's a given. You have to verify the Biot number. Then, if it is an infinite solid, usually only one dimension is generally provided, because that is the only one which is needed for you. So one dimension is provided. For the rectangular slab, one dimension, that is the thickness, is provided. For the cylinder and sphere, the radius is given. Okay. Then if it is a semi-infinite solid, the size is huge, and usually no dimensions will be provided. Generally, sometimes may be provided, but most of the cases, the dimension will not be provided. You will be using the words, you will be finding the words in the problem like very, very large, huge, or very thick object. So that is a hint for you, and to understand that it is a semi-infinite solid. But you will also, if you are able to calculate the Biot number, you should always calculate the Biot number and confirm whether it is a lumped or not first. And then if it is not lumped, then it can be infinite solid or a semi-infinite solid. So for that, you will have to use, if it is a semi-infinite solid, for you to use the Heisler's charts, you will have to confirm whether the Fourier number is greater than 0.2 or not, because the Heisler charts are applicable only when the Fourier number is greater than 0.2. For less than 0.2, you have to go for the infinite summation series equation. And usually in the examination conditions, we won't ask. So in the examinations, only the chart solutions are available, are prescribed for you. Okay. So I will stop here because the time is up. And we will continue tomorrow. Tomorrow I will take up solving some couple of problems. I will start with the infinite solids so that it will be easy to solve. Okay. So I think there are 75 students present. Should I take the attendance? All right, I'll skip the attendance for today's class then. Okay. So if you have any queries related to today's class or tomorrow or the cat one, you can ask now. Of course, you can verify your marks, and if you have any query, you can always apply for re-evaluation. Okay, please do that.